This is video number 2 about Hamilton graphs or Hamiltonian graphs. And we learned last time that a graph is Hamilton when it contains a Hamilton circuit. That is a circuit, or a cycle rather, that goes through every vertex of the graph. So in this video we want to learn some tests for us to distinguish when a graph is Hamiltonian or not. So here are a couple. So first of all, if G is not connected, then it's certainly not Hamiltonian, right? How are you going to get from one vertex to the next, right, in a graph that has a couple of different pieces, right? So say you have this, and these are two components of your graph. Well, how on earth are you going to start a cycle over here and be able to hit all of these vertices? Well, you're not going to be able to. Okay, so if it's not connected, then for free, you know it's not Hamiltonian. Okay, the next is if it has a cut vertex, not just if it's not connected, but if it has a one vertex cut, right? So a cut vertex, remember, is a vertex whose removal disconnects the graph. So in this case, that's this vertex here, V, we'll say. If it has a cut vertex, it's not Hamiltonian. And this also sort of makes sense if you think about it. If I start on the one side of the cut vertex, so let's imagine that I sort of travel here and here. Well, now, as soon as I get to the cut vertex, I can either choose to close the cycle, but that's not going to be Hamiltonian. If I go to the other side, then there's no way for me to ever get back to this vertex, right? Because you're not allowed to repeat vertices in a cycle, so as soon as you use that cut vertex, you can never use it again to go back to the other side. Okay, so this is not going to be Hamiltonian. Okay, so what is actually happening in these two things? In some sense, you want to have enough passages from one quote-unquote piece of the graph to another. So what that is more specifically, so the general term, or the general idea of what's happening above, is that if the number of components in G delete S for some subset S is more than the size of the set S, where S is some subset of vertices, then G is not going to be Hamiltonian. So what's happening here is, in the first part, S is empty, okay? So like you removed 0 vertices, but you have 2 components. Okay, well that's not okay. And then here, right, if we remove one vertex, the vertex V, right, we'll be left with 2 components, right? If we removed V, we would have this graph left. So here, in purple, the set S is the single vertex V, and when you consider G delete S, that's what this subtraction means. When you consider G delete S, this is the graph you get. It has 2 components, but that's bigger than the one vertex we removed. So we know that this is not going to be Hamiltonian, right? Because we removed one vertex, and we ended up with 2 components. That's not okay according to this inequality. So let's see a slightly more complicated example. So let's think about this graph here in purple and this vertex cut. If we remove V1 and V2, we get just sort of these outside edges. Right, we'll have this edge and this edge and this edge, right? Because all these interior edges are related to V1 and V2. So here we've removed 2 vertices, and we get 3 components, and according to this inequality, that's not okay. And if you think about what's happening here, let's just try to build one of these, a Hamiltonian cycle. So let's say we start here and we go along. Okay, now we use V1. And when we use V1, that's one of the 2 pathways between these 3 pieces. Okay, so for example, I could take it down here. And so now I've traveled from this piece down to this piece. Okay, and so maybe I use this edge. And then when I use V2, now I'm traveling again between these 3 things, these 3 singleton edges. Okay, so let's say I go here. Well, now I've used the only 2 pathways that connect these 3 pieces, right? So there are sort of these 2 phantom vertices in here that are the only ways to get between these 3 pieces of the graph, and I've already used up both of them. So how on earth am I going to get back to my original starting place? I would have to repeat one of these 2 pathways. So essentially what this says in purple up here is that if you remove a couple of vertices and you end up with more components than vertices removed, then that's not okay, because you're not going to have enough leeway to get between all of these pieces to hit every single vertex and get back to where you started. Okay, so that's another test that's not quite as easy as the first two, but it sort of encapsulates both of them. Okay, so now let's switch gears a little bit and think about a different result. So if G is a simple graph, remember that's one without loops and parallel edges, and it has at least 3 vertices, if the degree of U plus the degree of V is at least the order of the graph, okay, so N here, this N is the order of G. So if you take 2 vertices and their degrees sum to be at least as many vertices as in the graph, and if that's true for every pair of non-adjacent vertices, right, vertices that aren't connected, then that means that G is Hamiltonian. Okay, now that's kind of confusing. So instead of looking at this right away, let's just consider something else that sort of comes from this theorem. And that's the idea of the closure of a graph. Okay, the closure of a graph, which we denote with a C of G, is obtained by adding edges to non-adjacent vertices that meet this criteria up here in red. So if the degree of U plus the degree of V is at least the number of vertices in the graph, then we add an edge between them. And we keep doing that, and that process gives us the closure of the graph. Right, so officially, right, obtained by recursively joining pairs of non-adjacent vertices whose degree sum is at least n. So let's see what this means in practice here. Okay, so here I've got some graphs coming up here, and we're going to just do a couple of these, where here we're going to start with this graph G on the left, and then we're going to draw in the appropriate edges for the closure. So in this first one, the order of G is 4, right, 4 vertices. So we want to consider pairs of vertices that aren't connected. Okay, so for example, if I let this be V1, V2, V3, and V4. V1 is already connected to V2, and V1 is already connected to V4, so I don't have to think about those. What I do want to think about is V1 being connected to V3. So the degree of V1 is 2, the degree of V3 is 2, and 2 plus 2 is at least 4, the order of the graph, so that means that I should add this edge, right? Because degree of V1 plus the degree of V3 equals 4, which is at least the order of the graph, right? The order of the graph here is 4. And similarly, V2 and V4, right? V2 has degree 2, V4 has degree 2. They aren't connected, but when you sum up their degrees, you get the order of the graph. So this gives us K4, right? And so we know we can't add any more edges here. This is the complete graph on 4 vertices. Okay, so let's see if anything happens in the next one. So this was a 4 cycle. Now let's consider a 5 cycle. Okay, again, we only want to add an edge if you can choose 2 vertices that aren't already connected, like for example, maybe these two, and if you sum their degrees, you get at least the order of the graph. So if I take this vertex, it has degree 2, and this vertex, it has degree 2, and if I add them up, I get 4, but here the order of the graph is 5, so I don't want to add that edge because they don't meet my criteria for adding that edge. And you can sort of see this is a symmetric situation, right? Any 2 vertices you choose that aren't adjacent are only going to have degree 2 because every vertex has degree 2. So in this case, the closure of the graph is exactly the same as the original. So we don't need to add any edges. All right, so now let's try one more just so we're on the same page here. So you may want to try pausing the video and see if you can complete the closure of this graph. Okay, so let's think about what's happening here. This has degree 3, this has degree 3, degree 2, degree 5, degree 2, degree 3, degree 2. And the order of the graph, the order of G is 7. Right? 1, 2, 3, 4, 5, 6, 7 vertices. So if there are any vertices that are not adjacent to one another, and their degree sums add to be at least 7, you should add that edge. Okay, So a good way to think about these in general is to start with the vertices of highest degree. Okay, so here's our vertex of degree 5. That's the highest one. And we see that 5 is already connected to this vertex. It's connected to this. It's connected to this. It's connected to everything except this one, right? There's no edge connecting these two vertices. And if we're thinking about the closure, should there be? Yes, because the degree of this is 5 plus the degree of this is 3. That's 8, which is at least as many vertices as is in the graph. So when we consider the closure, we should have this edge. Okay, and when we do that, now, right, we're considering the degree of this being 4. Okay, this is what it means when it says recursively adding the edge, and now this is going to be 6. So now we're thinking about adding edges to see if the degree vertices in this graph meet our criteria. Okay, well now we don't have to worry about this high degree vertex anymore. Why is that? It's because it's already adjacent to every other vertex, right? It's already got an edge to everything else. And so you're never going to add like a multiple edge. It's only for non-adjacent pairs. Okay, so let's go to our next highest degree, 4. Okay, well, it's already connected to this one and this one and this one and this one, so we don't have to worry about those. So 4 plus 2, is that at least 7? No, it isn't, so we're not going to add that edge. How about 4 plus 3? Is that at least 7? Yes, it is, so we are going to add this edge. Right? And then we bump up the degree. Now this has degree 5, and this has degree 4, right? When we add in this edge. Okay, and again, we want to stick with our highest degree vertices. Well, now this degree 5 vertex is connected to everything except this degree 2 vertex. Well, is 5 plus 2 at least 7? Yes, it is. So we want to add this edge as well. Okay, and when we do that, this becomes a 3, and this becomes a 6. And now we don't have to worry about this one anymore either because it's adjacent to everything now. So you go to your next highest degree vertex, 4. So 4 is already connected, right, to this high degree vertex and this high degree vertex and this degree 3 vertex and this degree 3 vertex. So you only have to worry about these two degree 2 vertices. And 4 plus 2 is 6, which is not 7, so you're not going to add either of those two edges, right? And then you can keep going, but you'll see that when you're, as soon as you get to a vertex of highest degree where you can't add anything, then you can pretty much stop. Because now if we go to degree 3, right, well, if these edges couldn't be formed even with degree 4, then they certainly can't be formed with degree 3. So it turns out that this is the closure of the graph, the original graph on the left. So let's go back here. If I consider this graph on the left, the closure should be add this edge, then you can add this edge, then you can add this edge. And this is the closure of this graph. So, going back up here to this result, we know that a simple graph of order at least 3, if this is true, right, if the degree of 2 non-adjacent vertices is at least the order of the graph for every pair of non-adjacent vertices, then the graph is Hamiltonian. Okay. It turns out that a graph is Hamiltonian if and only if its closure is Hamiltonian. So if you're trying to figure out if a graph is a Hamilton graph, right, a Hamiltonian graph, then basically what you are doing, you can just imagine taking the closure, which will give you sort of more options, right? If you were trying to get from one vertex to any other vertex inside this graph on the left, well, if you give yourself more options, it seems like it should be easier to find a Hamilton circuit now, a Hamilton cycle now. But it turns out you can find a Hamilton cycle in this graph exactly when you can find a Hamilton cycle in this graph. And basically, the reason this is true is if you think about taking a graph and adding edges in the closure, if you take this graph G, if this is true, if degree of u plus degree of v is greater than or equal to n for every pair of non-adjacent vertices, then that means that when you add all the edges that would be in the closure of that graph, you're basically just going to add everything, right? Everything between these types of pairs of edges. Okay, so this operation of a closure, right? You need to know how this works. So if you need to go and rewatch these examples, that's fine. And then this theorem gives us a nice sort of clue for when something is Hamiltonian, because it can be easier to find a Hamilton circuit in the closure of a graph than in the graph itself. So this wraps up our discussion of Hamilton graphs.